the two speeds that we were asked for in part I of the question. So just to label that, we'll just call that part I. And back to what we're asked. In the second part, E is given to us as a half, and we're looking for the angle between the directions of motion after the collision. Okay, so this is where the trigonometry comes in. This is the last step in our list, trigonometry. And this usually comes in at the end. We've got to work out some angle, and we can draw a diagram for this. So after the collision, just draw the diagram of what's happening. We've just established that A after the collision, VA is going in this direction here. So let's show that in our diagram. And VB was very similar, except for a sign. He was going in the plus direction instead of the minus direction. So symmetry, it's just going off in this direction here. So we can put him going off this way. And the angle we're interested in is this angle in the middle here, the angle between the two. We'll call it theta. And so some trigonometry involved here. We'll call this one maybe alpha. And again, by symmetry, if this is alpha, it must be the same on the other side. And the first thing we notice is that the three angles together give us 180. So 180 is equal to 2 alpha plus theta. Again, what we're looking for is theta, so if we can find theta, it will be 180 minus 2 alpha. So now the problem reduces to finding alpha. And if we can find that, we can find the theta we're looking for. Now alpha, if we look at alpha here, we'll notice it's the same alpha as in this diagram up here. This is alpha. So we'll draw that diagram again. So VA is here. Alpha is in here. And the components we already know are minus UE over root 2 in the I direction. And it's U over root 2 in the J direction. So again, we get these from the table, or from our velocity here. U over root 2 in the J direction. And now hopefully we can see for the first time the way we can work out this alpha, because it's a right angle triangle, and we've got the opposite and we've got the adjacent. Just be careful with the minus sign, that's the only thing here. The tan of an angle, I want to emphasize the tan of an angle is always length. It's not just opposite over adjacent, it's length of opposite over length of adjacent. And length is the magnitude or the size. The size of the adjacent is U over root 2. Sorry, size of the opposite. Opposite over adjacent. The size of the adjacent, the length of it, to get rid of this minus, it's just UE over root 2. That's why the minus goes here. And now the U's over root 2 cancel above and below the line. And we're left with tan alpha is 1 over E. Which is 1 over a half, because we're given E as a half in this part. So we just label this again as part 2. This means that tan alpha is 2. And we're looking for tan theta. So tan theta is equal to, from this equation here, the same thing as getting the tan of 180 minus 2 alpha. And we now need to go to tables at this stage to use our formulas. So tan theta equals tan 180 minus 2 alpha. That becomes the tan of A minus B, and the formula from the tables for that is tan A minus tan B all over 1 plus tan A tan B. And the tan of 180 is actually 0. So we get 0 minus tan 2 alpha, which is simply minus tan 2 alpha over 1 plus 0. So it's just all evaluates to minus tan 2 alpha. And finally, we have an equation in the tables again for the tan of twice an angle. So it's minus into, it's 2 times the tan of the angle. So this is again directly from the tables, 2 tan alpha divided by 1 minus tan squared alpha. That becomes minus 2 times, now tan alpha we've already got, it's 2. That's minus 2 into 2 over 1 minus 2 squared, which is minus 4 over minus 3, which is 4/3. So the tan of theta is 4/3. In other words, theta is the inverse tan of 4 over 3, which is what we were asked to prove.